Okay, so now in this penultimate part of the lecture, we're going to estimate some GLMs in R using the data introduced at the start of the lecture. So to demonstrate practical application, we're going to estimate three models, one for each of the three distributions that we started the lecture with. First, we're going to estimate a Gaussian GLM using the London Underground journey time data that we've used in previous lectures. Second, we're going to estimate a binomial GLM using in the form of a logistic regression using the Titanic survival data. And in this example, we're going to try and explain the probability of survival in relation to a set of covariates. And thirdly, we're going to estimate a Poisson GLM using the M25 collision data, and we're going to try and explain variation in accident counts with respect to a set of covariates. So the R code is shown on the slide. The GLM function is included in the base stats library. We load the data with read.csv, shown here. That's our GLM data. And then estimation is just a one-line command, GLM rather than LM for the linear model. We've got the model formula, y of x, y tilde x, with an intercept included automatically. And this is what's different from the linear model command, though. We have a family argument which tells R which distribution the response follows. Gaussian for the normally distributed data, for the journey time data, binomial for the Titanic data, and Poisson for the M25 data. And then we have summary command to summarize the GLM results. So the R code is as simple as that. So let's look first at the output for the Gaussian GLM of the journey time data. Note the dependent variable is logged, as in lecture 6. We use that transformation to help meet the normality assumption, and we're still assuming a normal distribution since we've specified the Gaussian family in our GLM. This is the standard output R gives for any GLM. It gives the formula, it gives the deviance residuals with their quantiles, it gives the coefficient estimates with their standard errors and test statistics, the dispersion parameter, the null and residual deviance, and the AIC. And we'll interpret each piece on the next slide. The first observation to make is that these results are mostly identical to those obtained in lecture 6 using least squares. That is exactly what we should expect, since the maximum likelihood and least squares estimators are equivalent for a Gaussian response, as we showed in the estimation section. Going through the output, deviance residuals for a Gaussian response, the deviance equals the residual sum of squares, and the deviance residuals are equivalent to the least squares residuals in the coefficient are identical to the least squares estimates that we saw previously. The dispersion parameter for the Gaussian GLM is the error variance. Taking its square root gives 0.215, which matches the least squares residual standard error that we saw when we did this in the linear model setting. Then we have the two deviance statistics. The null deviance is the deviance of the null model, an intercept-only model. The residual deviance is the deviance of the fitted model. And we can combine them to get the portion of deviance explained, a generalization of R squared. The null deviance minus the residual deviance divided by the null deviance. Here, that would equal 0.72. So our model is explaining about 72% of the deviance relative to an intercept-only model. Finally, the AIC is reported, which we could use for model selection. The BIC can be extracted with the BIC command from other libraries. So the point I want to make with this first example is the Gaussian GLM gives us essentially the same results as the linear model. The normal distribution fits into the GLM framework just as the others do. Okay, next the Titanic data. We seek to model variation in passenger survival outcome in relation to a set of explanatory variables. The dependent variable survived is a binary outcome. 0 indicates did not survive, 1 indicates that the passenger survived. The independent variables are P class, the class of travel, first, second, or third, which is a factor variable, a classification rather than a number. Sex, male or female, a binary classification. Age, a continuous variable, which we enter as age and age squared to allow for nonlinearity, and SIB-SP, the number of siblings and or whether the passenger had a spouse on board. The idea being that having relatives on board may have been relevant to survival. So we estimate a logistic regression, a logic model, of the form shown. The probability of survival is the logistic function of the linear predictor, which ensures that the estimated probabilities lie between 0 and 1. Remember, that's precisely the guarantee a linear model could not provide. The linear predictor includes an intercept, 2 class dummies, 2 rather than 3 because the first class is the reference case, the sex dummy age, and age squared, and SIB-SP as shown in the final equation in the slide. And here is the R output. The structure is the same as before. Formula, deviance residuals, coefficients with standard errors, though note we now have Z values, the Wald statistics rather than T values. The dispersion parameter, which is 1 for the binomial family, the null and residual deviance, and the AIC. On the next slide, we'll focus on what's different in interpretation of the coefficients. So because the link is the logit, the coefficient values tell us the change in the log odds of the outcome for a 1 unit increase in the predictor. For example, for every 1 unit increase in SIB-SP, the log odds of survival versus non-survival decrease by 0.39. The standard error is small and the Z value relatively high, so we can take this result as significant. But interpreting results in terms of log odds is not very intuitive. What we'd really like to know is how the variables affect the probability of survival itself. And a useful way of doing that is via what's called marginal effects, shown here, which measure the change in the probability of survival when the independent variable increases by 1 unit. For a single continuous predictor in a logic model, the marginal effect is the expression shown. The derivative of the probability with respect to the covariate, which involves the logistic density times the coefficient in this form here. For a binary variable, the marginal effect is computed as a difference, the probability evaluated with the dummy variable switched on, minus the probability of it switched off. Note that the value of the marginal effect varies with the point of evaluation. Unlike in the linear model, there is no single constant effect. So using the MFX package in R, we calculate the marginal effects and average predictor values shown in the slide. Remember, the interpretation is now in terms of the probability of survival itself, not the log odds. So let's look at the results. Class of travel, being in the second class rather than first, decreases the probability of survival by around 0.275. Being in third class decreased it by 0.495, a substantial effect. So having a cheap ticket was not, in general, a good thing. Sex, being male, decreased the probability of survival by 0.568. And age, well, we entered age in quadratic form, and the marginal effects are harder to interpret here since age is really a single covariate rather than 2 separate predictors. What the model finds is a significant U-shaped relationship between survival and age. So the probability of survival was higher for the very young and the very old, and lower for those middle-aged people in between. And our final application I want to take you through is for the M25 collision data. In this model, we're seeking to model variation in road traffic collisions in relation to a set of explanatory variables. The dependent variable, RTC, is an integer outcome, the count of collisions on a link. The independent variables are AADT, average annual daily traffic flow, so how much traffic uses the link. T delay, the extra travel time under congested rather than free flow conditions, so a measure of congestion. Average speed, the average speed on the link, which we'd expect to matter for collision risk. And then 2 normalizing covariates, length, the length of the link, and lanes, the number of lanes on the link. Because longer links and links with more lanes should, other things being equal, record more collisions. So we estimate a Poisson regression model of the form shown there, and this is the linear predictor. It includes an intercept in the 5 covariates, which here are integers or continuous variables rather than factors. Here are the results, the same output structure once again. We have the formula, we have the deviance residuals, we have the coefficients with standard errors, z values and p values. From the Wald test, we have the dispersion parameter taken as 1 from the Poisson family, the null and residual deviance, and the AIC. And what we can see from this slide here is that all 5 covariates are statistically significant, so we can interpret these results on the next slide. First, overall fit. The proportion of deviance explained by our model is the null deviance minus the residual deviance over the null deviance. So 1701 minus 891 over 1701, which in this case is 0.476. So the covariates in the model are explaining a little under half of the deviance. For the coefficients, the log link means each coefficient tells us the change in the log of the expected outcome for a 1 unit increase in the predictor. An approximate interpretation we can make to this is that 100 times beta j gives the percentage change in the expected count per unit change in xj. So the Poisson model has quite a convenient interpretation. Going through the variables, annual average daily flow is positively associated with the expected collision count. We estimate about a 0.001% increase in expected collisions per additional vehicle per day. The units of AEDT matter here, and note that if we'd entered AEDT in log form, the coefficient would instead be interpreted as an elasticity. For delay, we find a positive association between delay and the expected count. Free flow conditions are, on average, safer than congested conditions, which seems to make intuitive sense. For average speed, we find a positive relationship, and scaling it up, a reduction of 20 km per hour in the speed limit is associated with approximately a 20% reduction in expected collisions. 20 times the coefficient times 100 gives about 21%. That suggests that speed reductions could be effective in reducing collisions, and the 2 normalizing covariates finally behave as expected. The expected count grows with link length, about 7.8% per additional kilometre, and with the number of lanes, about 20% per additional lane. So, I hope these applications have been helpful in understanding practically how GLMs work and they're estimated, and how they're interpreted, and of course how to execute them in R. And we'll return to practical estimation of GLMs in a later tutorial.